Hello, and welcome to the Scientific Adventures of Beardman. Today we're going to be looking at ways of measuring acidity. In our last video, we looked at the acidity of something is based on the concentration of the hydrogen ion, and that was in an inverse relationship, approximately inverse relationship with hydroxide ion. And the concentrations of hydrogen ion would be something like 4.28 times 10 to the negative 7th molar. Now, that's all great, and that's true, but if you're talking to a guy who's trying to figure out what the acidity of his soil is so he can grow the right plants, he's not always going to process 4.28 times 10 to the negative 7th and go, oh, well, that's this big, because most people aren't super comfortable with scientific notation. So it's much easier if we could take this number, 4.2 times 10 to the negative 3rd, 4.8 times 10 to the negative 18th. Okay, that's pretty small. But you get the idea. Take it and turn it into just one number. Okay, so well, which number is the most important? Well, if we look at the coefficients, the 4.2 or the 5.3, okay, well, if we go from 3 to 6, that makes it twice as big. But if we look at the exponent, 10 to the negative 3rd, 10 to the negative 6th, 10 to the negative 9th, going from 10 to the negative 3rd to 10 to the negative 6th, it's not getting 2 times smaller, it's getting 1,000 times smaller. So that number is really the crucial number, is that exponent. Okay, well, how do we get the exponent of a number? Okay, well, we could just look at it and get the exponent, but of course the number in front has some impact, okay? So we don't want to totally ignore that. So basically, if we take the logarithm, take the log of the concentration, then we'll get a number that ranges typically from 1 to 14. Okay? And that will give us a very nice number. Okay? So we get this equation, that what we'll call the pH, the power of the hydrogen, in other words, power like exponent to the power of 2 to the power of 3, power of hydrogen, equals the negative log of the hydrogen concentration. By making it the negative log of the hydrogen concentration, when we take the log of the hydrogen concentration, since this exponent is going to be the negative 3rd, negative 5th, and so forth, that negative will cancel out with the negative we put into the equation. So we'll have positive numbers, which, once again, is typically preferred by people. They prefer to think of the positive numbers. So now we've taken our concentration and transformed it into a pH. Well, we learned that things with negative 7 or more, meaning negative 6, negative 5, negative 4, and so forth, were acidic solutions. So that means if we have a pH that is 7 or 6 or 5 or 4, which now we'll think of as less than 7, okay, then we have an acidic solution. So if your pH is 6 or pH is 3, if your pH is 1, it's a very strongly acidic solution, or strongly acidic soil, or whatever it is that you're measuring. If your pH is exactly 7, that would be 1 times 10 to the negative 7th concentration of hydrogen, which is exactly neutral. That would mean that the concentration of hydroxide is also 1 times 10 to the negative 7th. And then if we have a number bigger, if our concentration of hydrogen is 10 to the negative 10th, whatever, somewhere in that range, anything smaller than 10 to the negative 7th, then our pH will come out to a number greater than 7. Okay, 10 to the negative 10th would become 10, so a pH of 10 would be basic. So anything pH greater than 7 is going to be a basic solution or basic soil or whatever it is that we're measuring. Okay. Now we could also talk about the power of the hydroxide, okay, and look at the POH, far less commonly used, okay. but the pH of the hydroxide would be calculated the same way, the negative log of the hydroxide concentration, which would then give you basically inverse numbers to what you got from the pH. Well, in fact, as we can see, if we took 1 times 10 to the negative 7th and then 1 times 10 to the negative 7th, if we calculated the pH, that would be 7. If we calculated the pOH, that would be 7. And so together that would give us 14, which is our ionization constant, okay, is 10 to the negative 14th. So we can see that if we just take the pH plus the pOH, we get 14. Okay, so as the pH becomes 2, the pOH would be 12. Okay, because they will always equal 14, just like the concentration of hydrogen times the concentration of hydroxide would always give you 1 times 10 to the negative 14th, which of course when we take the negative logarithm we get 14, which is why that all works out. And because we're dealing with exponents, we're now adding pH plus pOH gives us 14. Whereas before we were multiplying the concentration of hydrogen times the concentration of hydroxide equals 1 times 10 to the negative 14th. The last thing is, because I know not everyone's super strong at logarithms, let me just reverse the equation for you. We want to find the concentration of hydrogen. That's going to equal 10 to the power of the negative pH. Okay, so if your pH is 2, the concentration of hydrogen is 10 to the negative 2. Okay, now you'll need to use your calculators if you have a decimal here. So if it's 10 to the negative 2.3, you can't leave your answer that way. Plug it in and you'll get 5 times 10 to the negative 3rd for the concentration of hydrogen. So once again, make sure you know how to use your calculators for that. And the same thing for the hydroxide concentration. You can find the hydroxide concentration by doing 10 to the power of the negative pOH. Okay. Once again, if your pOH is negative 2.3, then you do 10 to the negative 2.3, which when you plug in your calculator, you get something about 5 times 10 to the negative 3rd power molar for your hydroxide concentration. All right, let's do a sample problem. Okay, so what is the pH of a solution with a hydrogen concentration of 4.2 times 10 to the negative 10th molar? Okay, so if we're doing that equation, we're looking for the pH. We have the hydrogen ion concentration, and so we'll be using the equation pH equals the negative log of the hydrogen concentration. Then we won't have to rearrange because we just got a whole bunch of equations on your equation sheet. So we just plug in. We go straight to the plug-in step. pH equals the negative log of 4.2 times 10 to the negative 10th molar. And when we plug that into the calculator, we get pH equals 9.38. Okay, and so that would be our pH. Another sample problem, just doing it backwards now. So the pH of an unknown solution is 6.35. What is the hydrogen ion concentration? Well, now we use the equation. The hydrogen ion concentration equals 10 to the negative pH. So we plug into that equation. Hydrogen ion concentration equals 10 to the negative 6.35. We plug that into our calculator and we find out that the hydrogen ion concentration is 4.47 times 10 to the negative 7th molar. Okay, only slightly acidic. Okay, then if we had something a little bit trickier, what is the pH of a solution if the hydroxide concentration is 4.0 times 10 to the negative 11th molar? Since we have the hydroxide concentration, we can calculate the pOH. So pOH equals the negative log of the hydroxide concentration. So pOH equals the negative log of 4.0 times 10 to the negative 11th molar, which when we plug into the calculator, we get out 10.4 POH. Then we're asked for the pH, and so we can do pH plus POH equals 14. We have to subtract POH from both sides so that we're solving for pH. And that will give us 14 minus 10.4, which will leave us with, when we plug that in a calculator or do that in our head, we get 3.60, or 3.6 with significant digits. 3.6 is the pH. So that's the basic idea of how you calculate pHs, POHs, and how you can relate those to the hydrogen ion concentration or hydroxide concentration that we calculated in the last video. So that's all for pHs. We'll look forward to seeing you next time on the Scientific Adventures of Beardman. Have a great day. Remember, this is basic. Well, half the time it's basic. The other half it's acidic. See you next time.